quick recap of vectors. So position vectors. Okay, so there is a position vector which I've labelled U. Remember, OP is a position vector because it's anchored to the origin there. We could also write it as an ordered pair. We could write it as a column vector. Actually, sometimes ordered pairs, when it's written like that, are known as row vectors as well. You could call it a row vector, but anyway. Column vector, personally, I think is the best way of writing them. Or we could, of course, just break it into component form. So x in the I direction, y in the j direction. And we can find the magnitude of the vector. It's just the length of that. So distance formula, whatever, Pythagoras. Square root of x squared plus y squared. And the direction of the vector is the angle it makes with the horizontal. So inverse tan of y and x. So they're all the vector ideas. Now I'm going to talk a bit about space curves. So far with motion, everything's just been in a straight line, and that's the easiest way to analyse it. It's just looking at a straight line, because then we only have two directions that we have to think about. So consider this. We've got our position vector, and it's some function of t, probably time for what we've been looking at, so it might be something like that. Now, as t changes, obviously my vector's going to change. And if I was to draw in another one, so there it is after some change in time, it's over there at Q. At another time, it's over there at R. But if I was to plot in the endpoints of all of those vectors, I'd get some curve. That's what we call a space curve. That's, if you like, the path our particle is travelling on. So it's not a straight line. It's travelling in some sort of curve. If I want to work out the velocity at any point, that's fine, because velocity is still the derivative. But when we're talking about curves, what's the derivative measure? It's the slope of the tangent at that point. So the velocity vector will be the tangent at a particular point. So at P, my velocity vector would be going in that direction, tangential to the curve at P. I want to find velocity and acceleration. What makes life a lot easier is to break it into its components, because each of those components would be travelling in a horizontal or a vertical direction, but a straight line, I guess, is the key. It's easier to look at things travelling in straight lines. And that's why vectors are very useful, because we can get the point but break it up into its components, and as I say, each of those components will be a straight line, and then we use our vector analysis to solve any problem. So displacement could now be written like this. If it's not just moving in a straight line, I say, well, I can always break it into two components. And so there'll be some function going in the horizontal direction, some function going in the vertical direction, but these will be the two components of my displacement. And then velocity, I would just differentiate each component, and that would get me my velocity vector. And if I want to find the magnitude of the velocity, then I just find the magnitude of the velocity vector. Square root of the horizontal component squared plus the vertical component squared. And if I want to know the direction it's travelling in, then it's the direction of the vector. Now this is an important bit. If ever you want to work out the direction of the particle, you must work with the velocity vectors, because the velocity is telling you where it's travelling. So that's where you get your direction from, the velocity vector. Acceleration, then I could differentiate each component again, and I'll get an acceleration vector. And if I want the size of it, once again, get the two components, work out the magnitude of the vector. So if I get something like this now, my particle's moving and I've been given the velocity vector for it. Minus 2 sine 2t in the horizontal direction, 4 cos 2t in the vertical direction. Given that, so initially, because that's when t would be 0, it's simply I. In other words, it's at the point x equals 1. Find the position vector at any time. We would integrate, but now I'm going to integrate each component. So if I just look at the x component, velocity in the x direction, dx to t is minus 2 sine 2t. Integrate that, well, I'll separate the variables. My initial conditions were t equals 0, we said we're at x equals 1, and then I'm finding a relationship between x and t. So no different to what we were doing, because now it's horizontal motion. And I eventually get, there it is, x equals cos 2t. But now let's have a look at what's happening vertically. But vertically, when t equals 0, y was equal to 0. Remember, we're at the point x equals 1. We're on the x-axis for this one. Integrate that one, and we end up with y equals 2 sine 2t. So the position vector then is cos 2t in the horizontal direction, 2 sine 2t in the vertical direction. Position vectors of two different particles now. So we've just got two different particles moving out there in space. We want to prove that these particles will collide, and when they're travelling at the same speed. So when they collide, they're at the same speed, but they'll hit at right angles to each other. If particles are colliding, they must occupy the same space at the same time. Simple idea, but that's effectively what must happen for them to collide. So if I have a look at the components, that means their x components are going to be the same. And if I solve that, I can get a value for time. But that's a cubic. Let's see if using the y component makes life easier. They've got to be the same as well. But this one gives me a quadratic, so I think I'm going to use that. That's got to be easier to solve than the cubic. I get two possibilities. It's either going to happen when at 1 second or 2 seconds, or maybe it happens at both. Let's substitute it now into the x component to see which one also works. But when I sub in t equals 1, I get -1. I don't get 0. So it's not happening after 1 second. Yes, they'll have the same vertical component, but not the same x component. So they'll be at the same height, but horizontally there'll be different distances apart. When I sub in 2, yeah, that one works. We get 0. Okay. We now know they collide after 2 seconds. Now we have to prove they're travelling at the same speed. There's my two displacement vectors. I want the speed. If I differentiate it, so I differentiate each component separately, and there's my particle B. So when t equals 2, we want t equals 2, sub it in. I've got the velocity vector at that point in time for both A and B. I can find the magnitude. The first one turns out to be 5, so does the second one. So yes, they're travelling at the same speed. Not the same velocity, but the same speed. Okay, we've got that. But the other thing was we wanted to show they hit at right angles. But because I'm using vectors, that makes life nice and easy because I can just use the dot product. We know if the dot product's equal to 0, the vectors are at right angles to each other. Use the dot product, sure enough, we get 0. So yep, there's the final part of that problem. They do collide at right angles as well. Okay. This was an interesting little question. It actually came from an Extension 2 paper, but it's still using the same ideas. Particles travelling along that curve there, O to E. We're just simply told the position vector is R, and they're using the bold R to represent a vector in this case. Its velocity is V, its acceleration is A. Which of the following, so it was a multiple choice question, is consistent with the motion of the particle? So all these dot products. So there's the path of the particle. I just picked one point and said, okay, there's a point. Now, at that point, one thing I do know for sure, I don't know the numbers, but I certainly know they're both positive numbers. I know that. The velocity would be going off at a tangent. If I look at the two components of that, they're both going in the positive direction as well. Well, that means r dot v would end up with a positive times a positive plus a positive times a positive. So whilst I don't know its value, I do know it's greater than 0. We also know it's slowing down. That's the additional piece of information I'm now going to use. What does slowing down mean? If it's slowing down, that means velocity and acceleration are in opposite directions. Therefore, the components horizontally and the components vertically, because if it's going in the opposite direction, it's now going down this way. So its components will be negative and negative. So I work out that dot product, I'm going to get a positive times a negative plus a positive times a negative, which must be a negative number. So whilst I don't know the numbers, I do know whether they're positive or negative. So r dot v being greater than or equal to 0, and a dot v being less than or equal to 0 would have been the correct option for that one.